So today I'm going to talk about lattice enthalpy, specifically lattice dissociation energy. So this is defined as the energy for 1 mole of a crystalline ionic solid to separate into its gaseous ions. It's important to know that there is such a thing as lattice formation energy, which is also sometimes called lattice enthalpy, and that would be the same value but with an opposite sign. So it's important to know which one in specific you're trying to solve for if you're doing a problem involving the lattice enthalpy. So the problem that we're going to use to talk about this concept is this one here that says to use the following information to calculate delta H lattice of magnesium fluoride, and it gives us a whole bunch of equations with their own individual enthalpies. And you might look at this problem and think this looks like a Hess's law problem, and I'm going to somehow be combining these individual enthalpies to find the lattice enthalpy, and you would be correct. The reason why you're doing that is because it's impossible to actually measure the value of lattice enthalpy in the lab. The only way to find that value is by using Hess's law to combine things that we actually can measure in a lab to find the enthalpy of the lattice. So the first one of these equations is the atomization energy for magnesium. So in order to calculate lattice enthalpy, you have to have individual ions combining to form the compound. So magnesium in its standard state is a solid, and we need to have ions of gas. So this atomization energy is the energy it takes to move magnesium from a solid into a gas. The next equation is also atomization energy, but this is because fluorine's standard state is as a diatomic gas, and although it's already a gas, they are combined together, so they need to separate in order to be used to find the lattice energy. The next one is the first ionization energy for magnesium. So this is the energy that it takes for magnesium to lose 1 electron and have a positive charge. Magnesium is an alkaline earth metal, so it doesn't want to have a +1 charge. It needs to have a +2 charge. So it also has a second ionization energy, which is higher than the first ionization energy. Fluorine needs to become negative, and so instead of ionization energy, it has electron affinity. So this is the value of energy for fluorine to gain an electron. So you might notice that this one is actually our first positive value here, and that's because the electron is being gained. Our last equation here is the overall equation for the formation of magnesium fluoride from the elements as in their standard states. So we are going to take all of this information and we are going to use it to build a Born-Haber cycle diagram. So we start off by building our diagram by taking the formation equation and sort of splitting it up so that we have our reactants as they start here and our products here. And we see that the delta H between the reactants and the products has a value of negative 1,123 kilojoules. So our arrow here is pointing down. The first way we need to modify this formation equation is to have the magnesium move from being as a solid state to a gas state. So this is one of those atomization energies, which has a value of 148 kilojoules. We have to have the same process happen for fluorine. Fluorine is already a gas, of course, but it needs to separate into individual atoms. The next energy that we have is the first ionization energy for magnesium. So this, of course, is the energy for magnesium to lose an electron and have a positive charge. This is followed by the second ionization energy of magnesium. So this is the second electron to be lost. So now magnesium has a +2 charge. Like we talked about before, fluorine needs to gain an electron, so this we call the electron affinity. So it's also important to notice here that we don't just have one fluorine remember our products here have F2, so there are 2 fluorines. We don't just have one fluorine, we have 2. So we need to multiply this value by 2 before we put it into our equation. So the rest of them were fine as 1, but this one, it needs to happen twice, so that's why we're multiplying it by 2. So this difference that we have from our products going to the individual ions as gases is what we call the lattice energy. And like I said, in specific, this is dissociation because we're going from the crystalline solid to the individual ions as gases. If you were going the opposite direction and you were looking for the formation, then you would be going from the gases down to the solid, and so you can see that the arrow would have the same magnitude, so it would have the same value, but it would have the opposite sign. So our value is going to be positive because our arrow is pointing up. If we were trying to, instead of find the dissociation, to find the formation, our arrow would be pointing down, so it would have a negative value. So to do our calculation, we just have to know that our lattice energy plus the energy of the overall reaction is equal to all of those individual enthalpies combined. So when we add all of those up together, remembering to multiply this electron affinity by 2, because that has to happen twice for fluorine, that is how we will find our lattice energy. And when we do the math, we find that the lattice energy for this particular compound is 2,970 kilojoules.